Good morning, Internet. I am Matt Buyak, and in this video, I'm going to write a class for calculating the prime factorization of a number. So in the last video, you may recall we solved problem number 21 from the Project Euler problem archive. And this problem involved finding the sum of divisors of a number. Now, for our solution to that problem, we basically just did brute force. But as I mentioned in that video, often that's not going to be sufficient. We'll need more sophisticated techniques. Also, the questions of finding the divisors of a number, finding the sum of divisors, finding the number of divisors, these are all very common tasks in Project Euler problems in general. And so rather than writing that code from scratch every time, we'd like to have, take that code and put it in a place where we can reuse it whenever we need it. And so that's going to be the point of this video. So let's get into it. So I'm going to be adding a new file to our number theory library. We'll call it factors.h. OK. And so just a quick recap for those of you who may not recall. There's a theorem which states, it's called the fundamental theorem of arithmetic. And it states that any positive integer can be written as the product of primes. So that is, you might write, n equals, p0 to the r0 times p1 to the r1 times times p, call it capital P minus 1 to the r p minus 1. And that product is unique. And so this is referred to as the prime factorization of a number. And if we know the prime factorization for a number, there are quite a few things we can calculate about that number very easily, such as the number of divisors, sum of its divisors, etc., etc. And so we will be writing a class for calculating this factorization. So we'll say class factorization. And we're going to need to include standard integer. OK, so in the public section, we're going to want a method factor. Just take an integer there. We'll also want a little helper structure here. Call it prime power. So you'll notice that this product is organized into prime powers. So you have this prime, p0 raised to some power times p1, the next prime raised to some power, etc., etc. And so we'll want this helpful little structure here for representing one of those prime powers. So we'll say prime and exponent. OK, so this method here will initialize the factorization from a given integer, and then once that factorization has been done, we need some way of getting the individual factors, and so I'm going to overload the square bracket operator. So you'll recall that often we'll have a vector of integers, my vec. And then you'll say this is getting the first element from that vector, or this is getting the second element. And so we're going to enable the user of our class to use this same square bracket notation with our class. And so we'll say const struct prime power reference. operator, square bracket, and that's going to take a size t as the argument type. We'll also need to be able to know how many distinct prime divisors our factorization has, and so we'll just say std size t size. Okay, so now for storing our factors, I just a moment ago mentioned the vector class, and that's what we're going to use to store our factors. So we'll say vector. Oh, and we will need to include that. So we'll say include vector. And that's going to be uint32t, or excuse me, no, that's going to be prime power. We'll call that factors. Okay, so I think that's enough to get started in terms of an outline of our class. Let's create the CPP file, factors.cpp, factors, plural, and include factors.h. Oh, one thing, I did not intend this to be a constructor. This should be void. And I think it actually will also be useful if we say uint32t n, and then we'll have some method. In theory, the user of our class could recalculate this value n from the factorization, but there's no reason to make them do that. We can just store that. So I think that will probably be useful. Okay, so we have our factor method here, and we've done this before in a number of other problems. I think, and maybe even as far back as problem number 3. Let's see if I'm, yes. You can see we, found the prime factors of this number here. And so if you're interested, you can go back and take a look at those videos for a little bit more detail. Otherwise, I'm just gonna hammer out the code here. Okay, so the idea is that we're going to have our divisor, call it div, and we're going to say for div is equal to 2, div is less than n, plus div. Let's see, we will need prime power. Yeah, I think that should be good. Okay, so we're going to try each of our divisors one at a time. So we'll say if n mod div is equal to 0, that is, if div divides n, then we want to add that to our vector of factors here. So we'll say pp dot x equals 1, pp dot prime equals div. And then we'll say, let's see here, n divide equals div. And then there might be more than one, or the exponent might be greater than 1. And so we want to try repeatedly dividing n by div and see how many times we can do that division. So we'll say while n is greater than 1, and n mod div equals 0. Then we're going to do pp.exp, increment that, and n divide equals div. And then after we've found, we've divided out all of that prime, then we can add that prime power to our list of factors. So then we'll just say factors dot push back pp. And now that I've just thought of it, we should at the beginning here say factors clear. I think that's the method. Okay, because we want to make our class reusable so that we can factor one number and then maybe we use it again and factor a different number, and in that case we need to clear the existing factorization. I'll also say n equals n. Okay, so I think that should be it for our factorization. Yes, I think that should be good. Oh, one corner case I just want to ponder for a moment here. I believe we want this to be less than or equal to n because in the case when we're left with a single prime, n is basically then divided out to just its smallest prime divisor, then div will equal n, and so we want to be sure to allow that that case. Okay, the rest of this code is fairly straightforward, so we'll say factorization, and we'll say return factors.size. And here we'll say factorization, and we'll say return factors IDX. Okay. So as I've mentioned in previous videos, we can't actually, our library has no main.cpp. So in order to actually exercise this code, we're going to need to add a test. So we'll say under tests, we'll call it factors test.cpp. And we can just grab the, if we go over to primes test here, just grab this out of there. Also, we'll grab these standard include files, put those at the top. Okay. We'll also need to add our factors class to the make file for our library. So if we go in here, we'll need to add at the bottom factors.o, depends on factors.cpp and factors.h, and we'll say just the standard build command here, And then we'll want to add that to our library. Okay. Now let's go over to our test. Okay, so the most straightforward way of testing our class here is just for every number between, say, 1 and 10,000, determine the prime factorization, and then confirm that each of the prime factors is actually prime, and that our prime factorization actually multiplies to give us the product that we expect. So that's going to be the approach for our test here. Let's first let's include factors.h. And we'll need to update the makefile here also. So let's just copy one of these. And we'll replace big int with factors. Okay. And we'll want to include factors test in our list of all tests. Okay, so let's say uint32t, and we'll just call this evaluate factorization. So this is just going to take a factorization that we've calculated and evaluate that product so that we can check to see if it actually gives us the expected value. Okay, so let's see. Say result, and say prime power pp in. Oh, actually, I don't think we can use this notation. I don't recall what the requirements for the for each syntax is, but I don't believe our class actually meets those requirements. I think you need it's a little bit more than just supporting the square bracket operator, as I recall. So we'll just do it the old-fashioned way. I equals 0. I is less than f dot size plus I. Let's also j. And then so we'll say for j equals 0, j is less than f I dot exp. Result times equals f I dot prime. Okay, so that's just iterating over, this inner loop is going to iterate a number of times equal to the value on that exponent, and just multiply our result by that prime that number of times. Okay, so now we can say I factorization f. We'll say for I equals 0, I is less than 10,000. Increment I. Oh, actually, we want this to start at 1. If you try to factor the number 0, bad things will likely happen. So let's not do that. Okay, so let's start by f dot factor I. And we want to confirm that that every prime in the prime powers of f are actually primes, and so let's include our primes.h. And we'll just say prime or primes p. Also need another index. Okay, so we'll say for j equals 0, j less than f dot size, increment j. And we'll say if not p dot is prime then we need to print some sort of failure message. So we'll say printf failure %u is not a prime. And go to end. Okay. Once we've confirmed that all the numbers, all the prime divisors are actually prime, we want to confirm that the product has the value that we expect. So then we'll just say if f dot, let's see, what did I call that? Get val. Yeah. If f dot get val is not equal to evaluate factorization f, we'll say printf failure yeah, we'll just say factorization has value %u expected %u, and then so the value that it actually has is going to be, oh, actually let's cache this. So we'll say uint32tn. So we'll say n equals that. Okay, so has value n, actually expected f dot, well, actually it's just going to be I. And then go to end. Okay, and then if we didn't hit any failure case, then we say printf success. All right, so let's make our, looks like we didn't actually build factors.o for some reason. Let's hop over to our makefile. We didn't add, we need to add factors.o to the dependency list also. Okay, there we go. And we have some build failures. Oh, it just looks like a typo. Factorization, there we go. Okay, and that succeeded. Hop over to our tests. Make. Looks like we did not build. We didn't actually define our get val method, so that should be easy enough. Just say uint32t factorization get val return n. Okay, and we have success. All right, so this is our basic prime factorization class. But there's quite a bit more that we can do with this. We're probably going to want code for calculating the sum of divisors, the number of unique divisors, that sort of thing. And there's some interesting analysis to go along with that also. So I'll plan to tackle that in the next video.